Hey everyone, and welcome. Today, we're going to dive into a story that sits right at the very heart of how science gets done. It's about a really common, but somehow widely overlooked, statistical flaw that could be affecting published research in some of the most respected journals out there.
Yeah, I know. That's a pretty intense question. But honestly, for anyone working in fields like psychology, management, or anything similar, it's a question we really have to ask. I mean, what if the very tools we depend on to tell us how important our findings are actually leading us down the wrong path? Stick with me because we are going to unpack this hidden problem and, even better, talk about a really powerful solution. All right, so our story really kicks off with something that every researcher is dealing with right now, this thing called the effect size dilemma. And believe me, it has completely changed the rules of the game when it comes to getting your work published.
You know, it used to be that just getting a statistically significant result was pretty much enough, but those days are over. Journals, especially the big ones in psychology and management, are demanding a lot more. They don't just want to know if you found something, they want to know how big it is. They're basically saying, show us your effect size, because that's what really tells us how much a finding matters in the real world.
And right here is the first big plot twist. Researchers are scrambling to meet this new demand, but there's one giant problem. The standard software packages that pretty much everyone uses for their stats, well, they often don't have the right tools for the job. This means researchers end up either not reporting effect sizes at all, or even worse, they're reporting numbers that are just plain wrong. And look, this isn't some tiny issue in a handful of obscure journals. We're talking about the heavy hitters, like psychological science and developmental psychology. A study back in 2004 actually found that researchers in these major publications were reporting incorrect effect size values. This is a big deal. It's a systemic problem that could be totally messing with what we think we know about some really important research.
So, that leads us right into the next part of our investigation, a hidden statistical trap. And it's lurking inside a very common, very powerful statistical method that I bet a lot of you use all the time. The scene of the crime, if you will, is moderated multiple regression, or MMR. You've probably used this if you've ever wanted to check if, say, the link between stress and performance is different for men and women, or for a treatment group versus a control group, right? It's the go-to tool for digging into those kinds of complex questions. Now, like any good statistical test, MMR has some ground rules, assumptions it makes about your data. And one of the most critical and most ignored is this mouthful: homogeneity of error variance. All that really means is the test assumes the amount of statistical noise, the stuff your model can't explain, is the same for all the groups you're comparing. So your model should predict things equally well for men as it does for women, for example. And this right here just nails the problem, doesn't it? In a perfect world, that statistical noise is perfectly balanced. But real data from real people, it's messy. And way more often than not, that noise is uneven. Your model might be way better at predicting the outcome for one group than another. And when that happens, the assumption is broken, and the results you get can be totally skewed. And hey, don't just take my word for it. As Aguinas and his colleagues were pointing out way back in 1999, this assumption gets violated all the time. And the scariest part is that it's often unbeknownst to researchers. It's this silent flaw that's been undermining results for decades. So what in the world are we supposed to do about it? Well, this is where the story gets good. Faced with this hidden flaw, a group of researchers decided they couldn't just sit back. They needed to build a better mousetrap. It was time to develop a new formula that could actually handle the messy reality of data. So here's exactly what goes wrong. The main number we use for effect size in MMR is called f². But when you have that unequal statistical noise we talked about, the standard formula for calculating f² is, to put it bluntly, just wrong. It's not the right tool for the data, and it can spit out a number that's way off, either making your finding look bigger or smaller than it really is. And here's the turning point. In a 2005 paper, Herman Aguinas and his team rolled out the solution. They actually derived a brand new modified formula for f². And this new formula was built tough. It gives you an accurate number even when that critical assumption about equal noise is broken. This was a massive, massive step forward. Okay, but let's be real. A super complex formula buried in an academic paper isn't going to help the average researcher trying to get their work done. So the next and maybe most important step was to turn this awesome theory into a practical tool that anybody could actually use. And that is exactly what they did.
To close that gap between theory and practice, the authors of the paper we're discussing today built a free, super easy-to-use computer program. Its only job is to do the heavy lifting, running all those complex calculations for the new formula, making it totally accessible to any researcher, no matter where they are. And they made it so simple. You don't have to be a stats genius. It's literally 4 steps. You tell it how many groups you have, pick your data type, pop in a few basic numbers for each group, and bam, you click calculate. The program handles all the hard stuff for you. And the best part? They designed this thing to be for everyone. It's totally free, so no budget issues. It's written in Java, so it runs on pretty much any computer. Windows, Mac, whatever. You can use it online or download it, and it's even flexible enough to handle up to 10 different groups. They really thought of everything to make this solution easy to adopt. Okay, great. You run the tool, you get your new accurate F-squared value. But that brings us to the final and maybe most important question. What does this number actually mean? An effect size, all by itself, is really just a number. An F-squared of, say, 0.037 tells you that your moderator explains 3.7% of the variance. Okay, but is that a lot? Is that a little? Is it a big deal? To have any idea, you need context. You need to see how your result stacks up against everything else that's been found in your field. And this is where the work gets really cool. The researchers provided that context by reviewing 30 years of studies. They calculated the new F-squared for hundreds of effects and created these benchmarks. What did they find? The average effect size was just 0.009. That's tiny. And half of all the findings were even smaller than that. So now let's circle back to that example value from the paper. An F-squared of 0.037. Looking at it alone, you might just shrug. But now we have the context to really understand it. When you put it into perspective, that 0.037 is more than 4 times bigger than the average effect size found over 3 decades of research in top journals. All of a sudden, that little number looks like a giant. Being able to say your finding is 4 times the norm, now that's a powerful statement about its importance. And that is really the heart of it all. This whole solution isn't just about fixing a statistical mistake. By giving you an accurate number and the benchmarks to make sense of it, this tool gives researchers the power to truly understand and explain the importance of their work. It helps us move beyond a simple significant or not significant and toward a real understanding of how much things matter. So, I guess this leaves us with one big lingering question, right? For years and years, people were unknowingly using a flawed method. Now that we have a better, more accurate, and totally free tool, what happens next? How many findings already out there might need a second look? And how much clearer could our science become if we all just started using the right tools for the job? That's definitely something we're thinking about.